Cornsham equation. But now what you say is the time-dependent Schrodinger equation is equivalent to, it's very simple to go from here to here, to this formulation, which is called the quantum Liouville equation, where you see at the end here on the right-hand side, you have this commutator. And rho is no longer just a function of space. It's actually a matrix. So everything here is an operator. It's a matrix. It's a density matrix. And it's described here. So everything is written in this framework. And so you again have apply a perturbation, and you see how the equation changes. And you put it in this form. You have this is now the change. This is what we're interested in, the change, if you remember, the variation. And that's the Liouvillean, which is this part corresponding to these two pieces, plus the this commutator between the rho 0, the initial rho, and the change in the potential. And so you essentially have two terms in here. And what is interesting is to write that in Fourier space. And eventually what you end up with an equation like this. And you want to solve, because you were interested in rho prime, you want to solve that. And if you, when the right-hand side is 0, it's simply an eigenvector. So it's but we're interested in the case where you have simply a perturbation, and you solve that for many different perturbations. So then in the end, there's a very special form of that Liouvillean, which is block form. I don't want to go into the details. But here is what is computed really in the end. You're computing these quantities. Okay, A is the Liouvillean I just showed you. This we're writing this as a matrix form here, but what it is an inner product of the omega minus A. So omega is some sort of frequency, inverse times a vector V. And then you take the dot product of that, so it's an integral of that with some function u. And you do that for many different u's and v's. So what I'm interested in is just taking one pair now, and we're interested in doing this calculation for one pair uv. And how do you do that? You do that, well, they have an algorithm, and when they talk to me, I essentially suggested a different way of doing it. The algorithm that they have is based on something similar to this. But here's the Longshaw's algorithm, which computes a bi-orthogonal basis of vectors. And everything now is going to be expressed in that basis. So you have a certain initial vector q1 and p1, and you apply this recursions here many times, and you get a tridiagonal matrix which expresses the operator A in that basis. Essentially, it's exactly what you have. You have two bases, P and Q, and the expression of that operator, the Liouvillean, in that basis is tridiagonal. So you can solve now by just inverting the tridiagonal matrix. And the inner products, so the inner products are computed on the fly. I'm going to just show how it's exploited here. So that's the relation we have from the tridiagonal matrix. It only says that the nice thing here is that for different omegas, it's the same expression. It's really the same Q. So you can do all of these calculations for the same factorization, the same Longshaw's vectors with many omegas. And that's the trick about this Longshaw's technique. So now here's what you do. You're interested in doing the inverse, in computing the inverse of. Okay, looking at the inverse of this times a certain vector. The inverse of this vector times a vector. So you're looking at solving a system and then multiplying by a vector. And that turns out to be essentially this expression here. So you only need to, this is what you're looking for. It's an approximation. This term tends to go to 0. So you have another tridiagonal matrix. Solve the system with this vector E1, which is a vector that has 1 on top and 0 everywhere else. And then you accumulate these products here. And then once you have the triangle solved, just do the inner product. It's very simple, and it costs almost nothing to solve the tridiagonal system. It's really, when you have a J, so the cost here is solving a tridiagonal matrix of size J's, order J, very inexpensive. And then you have this inner product to accumulate. That's just an integration. Okay, and you could do this for many omegas. You can plot these, all these sort of omegas. Okay, now here is an interesting thing which I, being a mathematician, I would never do, but it's an interesting trick. It's based on observation. They observed that this is probably observed by Dario Rocca, I think the student who worked on this, that these coefficients that you have here in the algorithm tend to converge. These beta and gammas tend to converge to fixed quantities. As you can see here, the plots of those quantities. And of course, the psi j's also tend to go down to 0. So the initial few of those would be enough. Take just a small number of those would be enough. So the idea is just to extrapolate. And that worked out really well in terms of cutting down the cost. So I will just show you what they do. So this is just explaining what I just said, taking a small number of, fixing a certain n, taking the values of those betas and the psi, and then extrapolating them, one to 0, the other one to the limit. And here's what happens if you compare with and without this extrapolation. This is without the extrapolation, and this is with the extrapolation. And so you can see here that you really have to go all the way down to get the same approximation, whereas here you get a very good picture right away from the beginning. Okay, now I'm basically just done with this part. This is done mostly by Dario Rocca, who visited here in 2006. He came for a few weeks, I believe. And this paper now is appeared in Journal of Chemical Physics. I just have to say a few things about software issues. As you see, we have had a lot of, when we worked on these things initially, and as well with Dario, there was we used to have a lot of postdocs and students working together to these things, and it involves a lot of coding. Currently, it's very hard to do that. Actually, I'm trying to find now postdocs to work on some projects, and it's very difficult. There is a serious crisis, I think, and I'm not sure that you agree with me on this, but it's really, in the US, there's, if you try to find a postdoc to work the way we did a few years ago, I think seeing that there are a lot of difficulties. There's a combination of things. One of them, there's the power is almost inexistent. Manpower is almost inexistent. The physics is becoming harder. And I mean, it's very hard to find people who would be knowledgeable in getting, for example, this sort of thing. So that the first part that I mentioned was someone who knew about FFTs, about the conjugate gradient, about the physics, how to get boundary conditions and things like that. It was a lot of details like that. You really have to have very good people to be able to manage all those things. And then, of course, you have physics that are of different nature that are mixing. They makes the simulations a lot harder. And the machines are becoming harder to program. And we think of, just giving here CUDA, but it's just one example. But we have to start recording things that we have done. We spent a lot of time putting effort into MPI, load balancing and so on. Now we have to do some other things, try to look at multi-core, try to see how you can combine these different modes of programming. So it's a much more complicated game than before. If you have any graduating people in your groups or whatever, please send them to me. I have posted an ad just now. Okay, thank you for your attention.